Good morning. I am Barnaby PORTELLI and I will be presenting the work carried out on resonant micromirror oscillation amplitude measurement and on digital actuation of these micromirrors. This work was carried out at the University of Malta, Department of Microelectronics and Nanoelectronics, and forms part of a project that the University of Malta is collaborating in, named ESRQ, which is a pentafinance project. First of all, a quick presentation overview. I will start with a background about micromirrors and their applications, including different actuation technologies. Following that, I will go over a new technique that we are using in order to measure the amplitude of oscillations of micromirrors. In this technique, we are using just one photodiode in the path of the reflected laser beam, which makes the system very cheap and simple to implement. I will then compare the results obtained with this system with a laboratory setup that we are using. In the following section, I will be presenting a comparison between three all-digital techniques that can be used in order to drive the micromirrors. These consist of fractional and divider technique, fractional and sigma delta divider technique, and dithering technique. A comparison between the three techniques was carried out after they were implemented on an FPGA. Finally, I will give an overview of the findings in the project. So, a bit of a background about resonating MEMS micromirrors. These are structures typically manufactured in silicon and coated in a reflective layer. When oscillating, they are used in order to steer optical beams, and they're used in applications such as pico projectors, IR scanners, and microscanning spectrometers. Different technologies can be used in order to actuate these mirrors. There are three main technologies that are typically used: electrostatic, piezoelectric, and magnetic. They all have their own advantages. However, in our case, you are using electrostatic actuation, since it's quite simple to implement in a single layer of silicon, and they also do not require a special layer during manufacturing. In certain applications, it is very important to measure the amplitude of oscillations of the micromirrors. For example, in the case of microscanning spectrometers, the oscillation amplitude relates to the spectral bandwidth that can be measured. Moreover, in some applications where a PLL is used in order to operate the mirror at exactly its resonant point, a feedback of the phase of the mirror of the phase between the mirror angle and the applied voltage is required. Several techniques have been proposed in order to measure the mirror oscillation amplitude. A very simple and common approach is to use a set of separate COM structures and then measure the changing capacitance in these COM structures. These require an extra area on the device, thus making it bigger and more expensive. An off-chip alternative would be to use a position-sensitive detector to measure the position of the laser beam reflected off the micromirror. However, these devices are expensive and bulky, so it does not make them usable for portable devices. Another approach is to use a 4-quadrant detector underneath the micromirror, which is illuminated by a light reflected off the mirror, in order to compute the mirror angle. This is quite simple. This is not as simple to implement, since it requires a 4-quadrant detector to be available underneath the micromirror. The proposed system uses just a single photodiode in the path of the reflected laser beam in order to compute the amplitude of oscillations. The figure shown here describes the proposed measurement system layout. It consists of a laser beam projected towards the rotating micromirror. The reflected beam scan projects a line, and the position of the spot over time is shown in the graph on the right-hand side. At the maximum angle theta, the position over the laser spot is marked A in the diagram. A photodiode is placed in line with the reflected laser beam, which means that the photodiode produces 2 pulses per cycle. This means that a pulse train shown in the bottom right-hand side is produced by the photodiode. This is fed directly into the FPGA. The simplest way to implement the measurement system for the photodiode signal is to use the center point of each pulse. Then, using the equations shown here, the amplitude of oscillations can be computed. As can be noted from the equation, it is quite nonlinear, and the inverse tangent makes it in such a way that it's very sensitive to small errors in timing measurement. Moreover, the pulses are quite short. In our case, they are typically around 25 nanoseconds. This means that a photodiode with adequate rise time and fall time is needed. It is also important to note that the rise time and fall time do not depend only on the photodiode specification, but are also dependent on the laser spot shape. The previous measurement system described relied on both the rising edge and falling edge of the photodiode signal. These the rise time and fall time of will not exactly be symmetrical, which means that that an error would be introduced into the system. As discussed previously, a small error in the system will have a large effect on the measurement. Moreover, a more accurate approach would be to use just the rising edge of each pulse in order to measure the amplitude of oscillation. This can be achieved using the two equations shown here. The equations are way more complex than the previous solution. However, they do improve the measurement accuracy. In order to simplify the FPGA implementation, a logic table was implemented for both these equations, thus making them very simple to implement and quite fast. This is an image of the optical setup used in order to test the performance of the proposed technique. The source used was a helium neon laser, which passes through a beam splitter cube before reaching the micromirror. The reflected beam, once reflected off the mirror, the beam is again split in the beam splitter cube. One of the beam reaches the PSD while the other proceeds to the photodiode. This means that the setup can measure the mirror amplitude of oscillation using two different techniques at the same time. This is very effective way in order to compare the performance of the two techniques. The proposed measuring setup was implemented on a Spartan 6 FPGA, where the output of the FPGA was used to directly drive the high voltage amplifier. Feedback from the photodiode was buffered through a comparator before entering the FPGA. A Hamamatsu PSD was used as a reference in the measurement. In order to compare the performance of the system over a large amplitude range, a frequency sweep was used around the resonant point of the micromirror. As can be seen from the graph, the results from the photodiode signal matches quite accurately to the signal from the PSD. Now, in the next section, I'll be discussing all digital driver implementation for actuating the micromirrors. This type of micromirrors have a very high quality factor, which equates to 1 arrow bandwidth. In our case, this was typically around 20 Hz. Using only integer dividers, it is not possible to achieve the frequency accuracy required in order to operate this mirror at a resonant point. A solution is to use a digital to analog converter and a voltage controlled oscillator in order to synthesize the required frequency. This introduces the need of analog circuitry in the driver. This introduces the need of analog circuit in the driver, which increases the size and cost of the final product. Three different all-digital implementations were considered. These consisted of fractional and divider, fractional and sigma delta divider, and the Turing approach. I will start by going over the fractional and divider. This type of divider uses two separate integer divisions with values of n and n-1, and then switches between these two divisions during a time window. The ratio between the two integer divisions is chosen in such a way that the center frequency of the synthesized output is at the required frequency. This allows the system to achieve a frequency resolution which is way higher than what can be achieved using integer divisions. However, this technique introduces pairs adjacent to the center frequency in the spectral response of the output. An improved approach is to use a fractional and sigma delta divider. Similar to the previous approach, a divider which can switch between n and divide by n and divide by n-1 is used. However, instead of using a timing window to choose between the two divisions, a sigma delta modulator is used. The output gain has a high resolution, which is better than what can be achieved with integer divisions. In this case, the sigma delta modulator randomly distributes between the two integer divisions, which means that the pairs are shifted away from the center frequency, and therefore makes them less likely to affect the system. Finally, the third technique that we will be testing consists of the dithering technique. This technique again switches between two integer divisions in a pseudo-random pattern. This is achieved using the following procedure. First of all, you set up a target which is equal to 1000 multiplied by the input frequency and divided by the output frequency. When you then use a counter, but instead of counting in steps of 1, you count in steps of 1000. If the counter is greater than the target, then the target is subtracted from the counter and the output is toggled. Since the output is not set to 0, but instead the target is subtracted from it at the start of the next cycle, the initial value of the counter is the difference between the previous value of the counter and the target. This initial value keeps increasing over each cycle until it's larger than the step size. In this case, the cycle length will be shorter since the target will be reached in an earlier time. The setup used in the previous section was again used to test the three different all-digital drivers. The results on the top left-hand side show the minimum and maximum frequency response amplitude for a window of 1 second. In the case of fractional divider, there is a big difference between the minimum and maximum. This can be further seen in the results on the right-hand side, where the difference between the maximum and minimum is shown for the three techniques. For the case of fractional and sigma delta dividers, the dithering approach and the dithering approach, the difference between the maximum and minimum is very small. The results show that the fractional divider approach is not suitable for operating the micromirror in a stable fashion. However, both fractional and sigma delta divider and the dithering approach are equally good. The results were confirmed using phase measurement shown in the lower two graphs. We also analyzed the frequency spectrum of the output of the driver. As can be seen in the plot, both the fractional and sigma delta and the dithering techniques push the spares away from the center frequency. This means that the spares are outside the bandwidth of the micromirror and therefore do not affect it. In order to conclude, a setup that uses photodiode pulse timing in order to measure the mirror oscillating amplitude was demonstrated. The results show that the photodiode setup is comparable in performance to PSD setup, while being a lower cost solution. 3 all-digital frequency synthesizers were tested on the micromirror and their performance compared. Using fractional divider in order to synthesize the drive signal resulted in mirror instability, which means it cannot be used. While fractional and sigma delta dividers and the dithering technique are equally good in operating the mirror, the dithering technique is simpler to implement. Finally, I would like to thank my colleagues in this project. I would also like to thank the organizer of this conference for making it happen, and thank you for your time.